Swayam Prabha. Digital India. Educated India.
So, we will start today with the topic tuning of control parameters. Tuning of control parameters. We have discussed earlier three different control schemes: P only controller, PI controller and PID controller. For P only controller, one tuning parameter is there, that is Kc, proportional gain. In PI controller, two tuning parameters are there. One is Kc, another one is tau y. Tau y is the integral time constant. And for PID controller, there are three tuning parameters: proportional gain Kc, integral time constant tau y, and derivative time constant tau d. So, these are the tuning parameters. When we will go to apply the control equations, we need to use the values of these tuning parameters so that we get best possible closed loop performance. Fine. If we take a simple example, where we make a plot between closed loop process output yt and time t. Now, in this process, a step change in set point value is introduced. This is the set point value. Fine. We are getting this type of closed loop response. For a particular set of tuning parameter values, and if we use another tuning set, we get, suppose, this type of response. Say this is a one type of response and this response is, suppose, A2, where A1 and A2 are two closed loop responses, two closed loop responses provided by two tuning sets of a controller. A1 and A2 are two closed loop responses provided by two tuning sets of a controller. We get response A1 when we consider Kc1 and tau y1. Suppose this is the closed loop response of a process under PI controller. Fine. This is the closed loop response when the process includes a PI controller. So, PI controller has two tuning parameters, one is Kc, another one is tau y. Now, we get A1 response when we consider Kc1 and tau y1. We get the response A2 when we consider another tuning set, namely Kc2 and tau y2. Fine. So, the closed loop response varies with the tuning parameter values. Now, there are different criteria based on which we need to select the tuning parameter values. Suppose our first criteria is to keep the rise time as small as possible. Our target is to keep the rise time as small as possible. This is our target. So, which tuning set we will prefer? Kc1 and tau y1. So, if this is our target, I mean if we need to keep the rise time as small as possible, then we will prefer the tuning set corresponding to A1. I mean we prefer Kc1 and tau y1. Now, suppose another criteria is keep the overshoot as small as possible. Keep the overshoot as small as possible. So, if this is our target, which tuning set we will use? Second tuning set, I mean Kc2 and tau y2. Agree? Like this, there are different characteristics features. Like rise time, overshoot, there are few more characteristic features. They are like settling time should be as small as possible. Another characteristics feature is decay ratio. Fine. Now, one thing is clear that we are in dilemma in selecting the tuning set. Which one we will select, Kc1 tau y1 or Kc2 tau y2? Fine. Now, you see one thing, if our target is to keep the rise time as small as possible, then we need to consider the closed loop response at a particular time instant, and we will proceed to tune the controller. That means we can tune the controller considering the response at a particular time instant. Fine. But it will be nice if we consider the response throughout the operation period in selecting the tuning parameter values. If we consider the entire time period, if we consider the response throughout this time period, and if we tune the control parameters, we will definitely get better performance. So, in that way the time integral performance criteria is considered for tuning the control parameters. So, we will consider the time integral performance criteria, which takes into account the response throughout the period. Now, there are different time integral performance criteria. One is integral of the square error. Integral of the square error. IAC. It is represented as IAC equals 0 to infinity epsilon square t dt. Fine. This is basically not infinity, this is the time period for which or based on which we select the tuning parameters. Epsilon t is the difference between set point value of y and process y. Fine. This is the integral square error 0 to infinity epsilon square t delta t, epsilon square t dt. Another time integral criteria is integral of the absolute value of the error. Integral of the absolute value of the error, IAE, integral of the absolute value of the error. IAE is equal to 0 to infinity absolute value of epsilon t dt. This is the expression for IAE. Fine. Another time integral performance criteria is integral of the time weighted absolute error. Integral of the time weighted absolute error, which is denoted by ITAE, in short form ITAE. ITAE is written as ITAE equals 0 to infinity t epsilon t dt. Fine. These are the three time integral performance criteria which are used in selecting the control parameters values. Now, we will discuss the suitability of these three time integral criteria. Suitability. If we want to strongly suppress large errors, if we want to strongly suppress large errors, it is better to use IAC performance criteria. If we want to strongly suppress large errors, IAC performance criteria is used. It has this form. Now, if we square the error becomes larger. Therefore, this IAC performance criteria is used. If we wish to suppress small errors, then IAE performance criteria is used. Fine. If small errors are involved, IAC performance criteria is not used, because if you take square of small errors, this term becomes even smaller. Therefore, this IAE performance criteria gets preference when small errors are there, and when the errors persist for a long time, errors persist for a long time, then ITAE performance criteria is used. Fine. Now, we will consider the response of a process. Suppose this is indicating the set point. Now, this is the closed loop response. Now, it is obvious from this figure that as time progresses, the error decreases. So, as time increases, the error decreases, definitely for a stable system. Now, in the ITAE performance criteria, the time is multiplied with the error. It is written by this form, T multiplied by ET. Fine. Now, in this figure it is clear that as time increases, the error decreases. Now, if we multiply this time with the error, the entire process response gets weightage in selecting the control parameters. If we multiply this time with error, the entire process response gets weightage in selecting the control parameter values. Fine. Therefore, this ITAE performance criteria is used in selecting the control parameter values. Now, how we can tune the control parameters using this time integral performance criteria, that we will discuss with an example. How we can tune the control parameters by using these time integral performance criteria, that we will discuss in the next. So, in this example, first we will consider one closed loop block diagram, and in this example we consider a PI controller which has the transfer function GC equals KC 1 plus 1 divided by tau is. this is the controller block. For simplicity, we are considering ZF equals 1. And the transfer function of the process has this form, Gp equals 2 divided by S plus 1. This is the disturbance block, this is equals Gd. Output is y bar. For simplicity, again we are considering Gm equals 1. And error signal is going to the control block. Fine. This is the closed loop block diagram. Now we will try to derive the closed loop transfer function. The general form of the closed loop transfer function is written as y bar equals Gc Gp Gf divided by 1 plus Gc Gp Gf Gm y set point bar plus Gd divided by 1 plus Gc Gp Gf Gm dy. If we substitute all the individual transfer functions, then finally we get y bar equals tau is divided by tau square a square plus 2 zeta tau s plus 1 y set point bar plus tau y divided by 2 kc multiplied by s divided by tau square a square plus 2 zeta tau s plus 1 dy. If we substitute the individual transfer function expressions in this general form, we get this closed loop transfer function, where tau equals tau y divided by 2 kc and zeta equals half root over of tau y divided by 2 kc 1 plus 2 kc. You see, both tau and zeta are the function of kc and tau y. Fine. Now we will consider only the servo problem. We will consider the servo problem for tuning. Then the closed loop transfer function becomes y bar equals tau y s plus 1 divided by tau square a square plus 2 zeta tau s plus 1 y set point bar. This is for the case of this is plus 1 tau I s plus 1 divided by tau square a square plus 2 zeta tau s plus 1 y set point bar. This is the closed loop transfer function for the servo case. In the next we will consider a step change in y set point. In the next step we will consider a unit step change in set point. Accordingly, we can write y bar equals tau y s divided by tau square a square plus 2 zeta tau s plus 1 multiplied by 1 by s when we consider unit step change in y set point. Fine. Next we need to take the inverse of Laplace transform. If we take the inverse of Laplace transform, we get the expression for y in time domain. If we take the inverse of Laplace transform of this, then we get the expression for y as yt equals 1 plus 1 divided by root over of 1 minus zeta square exponential minus zeta t divided by tau multiplied by tau y divided by tau sin root over of 1 minus zeta square t by tau minus sin root over 1 minus zeta square t by tau plus tan inverse root over 1 minus zeta square divided by zeta. If we take the inverse of Laplace transform, if we take the inverse of Laplace transform of this equation, we get yt expression. Now, among the three time integral performance criteria, suppose we wish to consider IAC performance criteria. Fine. So, IAC is equal to integration of 0 to infinity y set point t minus yt whole square dt. Among the three time integral performance criteria, we are interested to tune the control parameters using IAC performance criteria. So, IAC is equal to 0 to infinity y set point t minus yt whole square dt. This y set point t is supplied externally by the person who is in charge of operation. This is supplied externally y set point t, and the expression for yt we have derived. So, for yt you use the derived equation. Fine. Now, what is our target? What is we required to do? What is required to do? Yeah, we the IAC should be minimized. With respect to tau and with respect to zeta. Fine. If we consider, if we minimize the IAC, we will get the optimum values of tau and zeta. If we minimize the IAC with respect to tau and zeta, we will get the optimum value of tau and zeta. Suppose these optimum values are tau star and zeta star. Fine. Now, what are the expressions of tau and zeta? The expression of tau and zeta we obtained previously as this is the expression for tau and this is the expression for zeta. Now, we will write tau star equals root over of tau y divided by 2 kc, and similarly zeta star equals half root over of tau y divided by 2 kc multiplied by 1 plus 2 kc. These two values tau square and zeta star we obtain by minimizing IAC. Now, we have the expressions for tau and zeta, those are written in this form. Now, you see we have two equations and two unknowns. We have two equations and two unknowns, tau y and kc. Solving these two equations, we can obtain the optimal values of tau y and kc. Solving these two equations, we get optimal values of tau y and kc. So, by this way, by using the time integral performance criteria, we can obtain the optimal values of tuning parameters. Fine. Similarly, we can consider PID controller, we can consider other time integral performance criteria, but the approach is like this. Okay. Next, we will discuss another tuning approach, that is Cohen-Kuhn technique. Now, so far we have discussed root through which test, we have discussed root locus technique and time integral performance criteria. First, we discussed root Hurwitz test. Fine. In this test, we need the process model in the form of transfer function. In the root Hurwitz test, we need the process model in the form of transfer function. Secondly, we started the root locus technique. The root locus technique, which is a graphical technique, and in the root locus technique also we need the process model, because for root locus technique we need to produce the plot by positioning the roots of the characteristics equation. So, for root locus technique also we need the process model, but these two techniques cannot provide the exact values of tuning parameters. These two techniques only can provide the range of the tuning parameters. These two techniques do not provide the exact values of tuning parameters. They only provide the ranges of tuning parameters. Therefore, they are not called as tuning techniques. It is better to call them instability technique. Fine. Thirdly, we discussed the time integral performance criteria. I mean controller tuning by time integral performance criteria. This technique requires the process model. This technique requires the process model, because in the time integral performance criteria we need the expression for yt. In the time integral performance criteria we need the expression for yt, that means process model is required, and this technique provides the exact values of the tuning parameters. This technique provides the exact values of tuning parameters. So, this is a tuning method. Fine. Now, based on this first point, we can say that it can provide better performance by using more accurate model. This time integral performance criteria involves the process model. Now, if we give more accurate model, we will get better performance. So, it provides better performance when we use more accurate model. So, therefore, we look for an efficient tuning method that uses empirical rules. Since the time integral performance criteria uses or depends heavily on the process model, we look for an efficient control technique that uses the empirical rules. So, next we will discuss one technique which is based on the empirical rules, that is Cohen-Kuhn technique or Cohen-Kuhn method. This method was proposed by Cohen and Kuhn. This is an empirical tuning method. This is an empirical tuning method. This method is also called as process reaction curve method. Process reaction curve method. Fine. Now, before discussing this method, we need to draw the block diagram. Closed loop block diagram. Say this is Y set point, this is controller output, this is the block for final control element, then the process disturbance process output. This process output is connected with the block of measuring device, and the measuring device output is Ym bar. Fine. Now, according to this Cohen-Kuhn method, the closed loop block diagram is opened by disconnecting the final control element from controller. According to the Cohen-Kuhn method, this loop is opened by disconnecting the final control element from the controller. Fine. Now, if we disconnect the final control element from the controller, then we can write the output Ym bar divided by input Cs bar, C bar S equals Gf, Gp, Gm. Definitely this is for the case of servo problem. Fine. Can we write the output Ym bar divided by the input C bar equals Gf, Gp, Gm, and this is the transfer function of the process reaction curve. Fine. Now, it is obvious that the output Ym depends not only on the process, it depends also on the final control element and measuring device. Fine. The output Ym depends not only on the process but also on the final control element and measuring device. Now, Cohen and Kuhn, they observed that for most of the chemical processes, they got sigmoidal response. Cohen and Kuhn observed that for most of the processes, they obtained sigmoidal response, sigmoidal safe. Like this. Suppose this quantity is B. That means the set point value, not set point, it may be the Y value at new steady state. B is the value at new steady state. For most of the chemical processes, Cohen and Kuhn observed that the process response looks like sigmoidal safe. Now, this response can be approximated by the first order plus date time. This is basically the response of a first order plus date time. Fine. So, we can write the first order plus date time as k exponential minus TdS divided by tau s plus 1. For most of the chemical processes, the response looks like this. Now, this shape can be approximated by first order plus date time, and this is the expression of first order plus date time response. The first order plus date time response can be represented by this equation, where K is static gain. So, what will be the expression for gain? Yeah, for most of the chemical processes, Cohen and Kuhn observed this type of response when a step change is introduced in C. Sigmoidal shape is obtained when a step change with magnitude A is introduced in C. Now, can you find the expression for K? Change in output, that is B, divided by change in input, that is A. Agree? Gain is the change in output divided by the change in input. Next one is the TD. TD is date time. Date time value we can obtain from this plot. This is the date time. Fine. Date time value we can obtain from the plot. Now, if we exclude the date time part, then the response becomes the response of the first order system. If we exclude the date time part from this response, then the response becomes the response of first order system. If we exclude the date time part from this overall response, then the remaining part is the response of first order system. Now, how much is this quantity? For a first order system, we have plotted y versus AKP versus T divided by tau p, and we got this equals 1. For the first order system, we plotted y divided by AKP versus T divided by tau p, and we obtained at time t equals 0 this quantity equals 1. So, how much is this quantity if we plot y versus t? This is tau. T divided by tau p equals 1, that means t equals to tau. So, this quantity is tau. If we consider the slope of this is s, the slope of this tangent is s, then we can write tau equals b by s. Can we write? If s is the slope of this tangent at starting from t equals 0, then we can write tau equals b by s. Fine. So, by this way we can determine all the parameters involved in this expression. Now, after finding the parameters of the expression, Cohen and Kuhn derived the empirical equations, introducing change in load variable. After finding the parameters involved in the first order plus dead time expression, Cohen and Kuhn derived empirical equations. Empirical equations, and they have derived the equations introducing change in load variable. For P only controller, they got the expression for Kc, where Kc equals 1 by K tau by Td 1 plus Td by 3 tau. For PI controller, they got two equations, one for Kc, another for tau y. This expression they got for Kc, and for tau y they obtained tau y equals Td 30 plus 3 Td by tau divided by 9 plus 20 Td by tau. For PID controller, they derived three equations, one for Kc, one for tau y and one for tau d. This expression they got for Kc. For tau y, the expression can be written as tau y equals Td 32 plus 6 Td divided by tau divided by 13 plus 8 Td divided by tau. And for tau d, they got tau d equals Td 4 divided by 11 plus 2 Td divided by tau. These empirical correlations Cohen and Kuhn derived by introducing change in load variable. Now, if you compare the three equations for P, Pi and PID, three Kc expressions, which one is the largest? I mean, which Kc is largest? Kc for P, Pi or PID? Kc value of PI controller is the lowest and Kc value of PID controller is the highest. Reason is very obvious. If we introduce integral action, there may be some instability problem. Therefore, Kc is taken lowest, and PID controller has better stability criteria. Therefore, highest Kc value for PID is considered. Thank you. The determination of Td